copper strip of width D, thickness T, carries a current I from top to bottom, as shown in the figure 1a. The strip is kept in a uniform magnetic field of flux density B, directed perpendicular and into the plane of the strip. Cross-sectional view of the same arrangement is also shown figure 1b. The charge carriers are electrons and they drift with drift speed Vd. Part A1. What is the direction of magnitude of force acting on electron E, shown in figure 1b? Copy the figure 1b into your answer script and clearly draw an arrow on the electron to indicate the direction of the force. Part A. I will draw the given diagram. Current is in downward direction. Current is in downward direction. Therefore, electron should move in. Current is in downward direction. Therefore, electron should move in upward direction. There is a magnetic field into the plane. Then we have to get the direction of force on electrons. We have to use the Fleming's left-hand rule. Force, magnetic field, current, FBI. Magnetic field is towards to the plane, and current is downward. Therefore, force should be in right-hand direction. We have to mark force F. It is A part 1. Then part 2. Now, if you replace the copper strip shown in figure 1b with another strip having a positively charged carrier, what is the direction of magnetic force acting on the positively charged carrier? If charge carrier is a positive, then current is not changing. Direction of current is in downward direction. Therefore, we have to consider force is in same direction. Part B1. As time goes on the copper strip described in A1 above, there would be a new equilibrium situation with regards to charges residing. Copy figure 2 into your script, answer script and illustrate this new equilibrium situation using plus to represent positive charges and minus to represent negative charges. A1 above, it means we have to consider electrons are current carriers. Therefore, there is a force on an electron to right hand direction. Then minus charges should be placed in this line and plus charges, relatively plus charges are in this line. Part 2 explain the reason have the equilibrium condition as mentioned in B1. Now I will consider an electron moving in upward direction. Current is moving in downward direction, therefore electron should move in upward direction. Velocity of electron, mean drift velocity, it is Vd. Now, when considering this electron, there is an electric field from plus to minus, and there is an electric force on the electron in opposite direction of electric field. We know that electric force is opposite to the electric field because of electron is a minus charge, or we can consider that it is attached to plus direction. Electric force, I will mark it as Fc, force of electric field, force generated by electric field. And there is a magnetic force in right hand direction as same as the first one. Then we can write there is an equal and opposite forces on electrons. We can write it magnetic force and electric force. Therefore, there is an equilibrium. Equilibrium means there is no movement for this electron in horizontal direction, but there is a motion in upward direction. It is the current flow. Then part 3, briefly describe how you would use this effect to verify that holes in a p-type semiconductor are positively charged carriers. We can check polarity of these two surfaces. We can write by checking the polarity of the side of the strip using this situation. A part 2 relative to the situation described in A part 1 for electrons. For the right side of the strip is positive relative to the left side. The charge carriers are positively charged holes. Or we can get if charge carriers are positive, part 3, polarity of two surfaces should be opposite. Then we can write directly by checking polarity of two surfaces. Part C1, derive an expression for the hole voltage VH in terms of VD, V and D. D is the VD, V and D. We can get for the equilibrium situation. Electric force should be equals to electric force on an electron in this direction should be equals to magnetic force in this direction. We can write electric field QE, charge into electric field. Magnetic field BQV, VD. VD means drift velocity. But we know that there is a BVD sin theta term for magnetic force, but magnetic field is perpendicular to the current. Therefore, it is 90, sin 90 is 1. We can cancel out Q and Q. Then we can write electric field. If the voltage drop between these two surfaces VH, we can write hole voltage divided by distance D, VH over D. We know that electric field intensity is potential gradient equals B VD. Then we can subject VH, hole voltage is B VD into D. In part 2, the current I flows through a conductor such as copper can be written as I equals NEAVD, where all symbols have their usual means. Derive the equation I equals NEAVD. We can consider the conductor. I will consider a conductor like this, and we know that current is charge flow rate, charge divided by time. When considering unit time, And when considering unit time, electrons should move Vd distance. Vd means velocity of an electron. Therefore, electron should move Vd distance for unit time. Therefore, we can consider conductor with Vd length. Therefore, for this situation, for a unit time, all electrons in this conductor should move out of this conductor. Then charge is charge of an electron into number of electrons per unit volume into volume of this conductor. Volume is AVD. It is the charge flow rate, charge per unit time. Therefore, time is 1. We have to consider that when time is 1, distance moved by electron per 1 second is Vd. Therefore, all electrons in this conductor part, Vd length, should be moved out to the conductor from this surface. So, this surface, it is depending on direction of current. Then we can get it I equals NEAVD. Vd means drift velocity. Part 2.1. Then part 2. Obtain an expression for whole voltage VH for the copper strip in terms of ENTIB. We have to substitute Vd from this equation to this one. Then I will subject Vd equals I divided by NEA. Therefore, whole voltage B, we can substitute Vd value is I over NEA into D. Then we can substitute area. Cross-sectional area is thickness into breadth. Breadth is considered as D. Then BI D over NE. Cross-sectional area is D into T. Then we can cancel out D. Whole voltage is BI over net. Then third part. Consider a copper strip of thickness 1 into 10 to the power minus 3 meters. In uniform magnetic field 0.5 Tesla. If I equals 48 amperes and VH 1.5 into 10 to the power minus 6 volts. Calculate the number of charge carriers per unit volume in copper. Take E value 1.6 into 10 to the power minus 90. We have to find the N value. Then we can subject N value by using this equation. I will subject N value. Then N value is BI over VH ED, ET. Then we can substitute values. B is the magnetic field in magnetic flux density 0.5, current 48, whole voltage 1.5 into 10 to the power minus 6, charge of an electron 1.6 into 10 to the power minus 19, thickness, it is given as 1 into 10 to the power minus 3. We have to simplify it and we can get the answer 10 to the power 29 per cubic meter. 10 to the power 29 per cubic meter. Number of free electrons per unit volume. Then part D. Cardiologist monitor the flow speed of blood through any artery using an electromagnetic flow meter. A schematic diagram of the 11 parts of such flow meters is shown figure 3. Blood plasma has a high concentration of sodium plus and chlorine minus ions moving through the artery with the blood at same speed v and same direction as blood flow. Assume that the ions in blood behave as charge carriers. Part 1. When the blood flows through the artery shown in figure 3, what is the polarity of electrode P? Give reasons for your answer. We have to consider magnetic force. Blood flow is towards this direction. P is this one and Q is this end. We have to get polarity of P. Blood flow is towards this direction. Velocity is marked as this one. Then we have to consider there is a magnetic field. I will draw the second diagram. Blood velocity is V. P and Q are this point and this point. There is a magnetic field in this direction, B. I will consider sodium ions. Sodium ions are plus. Then we can get direction of force by using Flemin's left hand rule, FBI. When moving sodium ions to this direction, it means current is towards this direction. FBI, B is in this direction, current is in this direction, force should be in upward direction. Therefore, force in upward direction, P is plus and Q is minus. Sodium plus ions are moving in upward direction. Therefore, we can write the answer positive. Polarity is positive. And we can write magnetic field, magnetic force on sodium plus is in upward direction. Upward direction. You have to write only the answer. Don't draw the diagram. Then part 2 is the flux density of uniform magnetic field applied to the system is B and diameter of the artery is capital D. Write down expression for the magnitude of voltage VPQ across two electrodes P and Q in terms of VBD. We can write it is like whole voltage. Then we can write VPQ should be equals to VVD. VVD. Then I will substitute given values. VPQ, V is magnetic field, V is the dip velocity, D is given as diameter of this artery is capital D. Then VVD. Part 3. If VPQ 160 microvolts, D 5 millimeters and B 2 into 10 to the power minus 3 Gauss. They have given that 1 Gauss is 10 to the power minus 4 Tesla. Calculate the value of speed of blood through the artery. We have to calculate velocity. Then I will subject velocity. VPQ divided by BD. We have to substitute values. VPQ is 160 microvolts. It means 10 to the power minus 6 volts. Divide by B is magnetic field. It is 2 into 10 to the power 3 Gauss. But 1 Gauss is 10 to the power minus 4. Therefore, we have to multiply by 10 to the power minus 4 to convert Gauss to Tesla. D is the diameter, 5 millimeters. 5 into 10 to the power minus 3 meters. then we can simplify it. Answer should be 0.16 meters per second.